this will Katharina Seitz from ETH Zurich. She's a doctoral student in hardware security. The title of her talk is 𝜇CFI, formal verification of microarchitectural control flow integrity. And Katharina spent several years as embedded software developer and formal verification engineer for functional safety at CERN and in the automotive field. Currently, she pursues a doctoral degree in hardware security at ETH Zurich in the computer security group, where she works on formal verification of CPU microarchitectures. Okay, then we're looking forward to your talk and the session.
Thank you for the introduction. Yeah, I will talk about formal verification of microarchitectural control flow integrity. CPUs are usually tested via simulation. And for security, usually via fuzzing. So you run a lot of programs and test many scenarios. But we all know security testing needs to be sure that there are no more bugs in the design, and simulation cannot guarantee that. With formal verification, we can achieve that. We can prove properties on a processor for arbitrary inputs. In the case of a processor, if we have the instruction bus as an input, it means if we prove a property, we prove it for arbitrary programs. However, it's often a CPU-specific and manual effort to write these properties. You write them over the HDL design, you write system Verilog assertions, and then use a model checker to prove them, and either are lucky to get a proof or you get a counterexample, which in case of security is a vulnerability. So we ask us the question, can we have a simpler solution than writing the properties manually? And to solve this, we developed 𝜇CFI, which is a generalized security property that can be used on different RISC-V processors, can be reused. Most of the verification is automated, and you can apply it early in the design cycle, so it doesn't rely on an already verified CPU. And this one property can capture multiple threat models at once. First, some definitions. When I talk about architectural control flow, I will mean the software control flow, where the program counter points to. So if we have a branch instruction, then the branch instruction decides what the next program counter will point to, meaning which instruction is going to be executed next. The microarchitectural control flow we now define as the clock cycle accurate values of the program counter. That means we look at the value at each clock cycle and also its update time. What could go wrong with the microarchitectural control flow? Let's look at some examples. Here we have a constant time program. We have 5 instructions, and only one of them reads secret data. This program is constant time on software level, following this constant time programming principle that no branches and no loads receive secret data. So we expect it to execute in a certain amount of time. And here, for example, if you pass operand 0 value to that add, it executes in 5 clock cycles on a specific CPU. But maybe on the same CPU, it executes this sequence of instruction executes in a bit longer time, in 6 clock cycles. So what's the problem here? Here we have a timing side channel. By measuring the number of clock cycles this sequence takes, we learn something about the operand. We learn that the operand is either all ones or 0. Here's another example of a program that is on architectural view, on software view, secure. We have an add that now reads attacker-controlled input. We have at the end an illegal instruction that creates an exception, and if everything goes well, then the CPU should go to the exception handler that is predefined. But there could be CPU bugs where if the operand of an instruction, for example, of the add, is passed to the program counter and thus directly writes into the program counter, there is a control flow hijack possible, because now if the add's operand was coming from an attacker's input, an attacker can now change the program counter. These are the kind of bugs we are looking for. With 𝜇CFI, we proved that these kind of bugs do not exist. We proved that the 𝜇CF has only ISA-specified deviations and ISA-specified data dependencies. This property is specified as an information flow from operand to the program counter. With the one property, we capture these 2 threat models. If we consider the operand of one instruction as a secret, and it changes the update time of the program counter, then information can leak via a timing side channel. Or on the other hand, if the same instruction would read data and we consider this as attacker controlled data and it can write into the program counter, then a control flow hijack attack is possible. So that's an information flow property. Information flow property in general is expressed like this. You have a source and a sink, and you want to verify that there is never an information flow from a source to the sink. Information means in this case data flow, timing flows, control flows, everything in the RTL. And in our case, it's the flow from operand to program counter should not exist, except if the ISA allows it. For the verification of these IFT information flow properties, we use celllift, which is a taint tracking logic developed by my co-author Flavio Solt. It's open source. And it's a logic that you take and augment the CPU with it. So it is like a shadow logic that tracks how information flows through the design. And the taint represents either the secret or attacker control data that we are interested to monitor. Celllift is implemented as a Yosys pass, and it duplicates the whole design. Every state is duplicated. Every state bit has a taint bit corresponding to it. And then for every logic cell, it creates like some logic that calculates how the information propagates through that logic cell. We then specify our CPU properties over this logic. I have here one example on how it works for an AND cell or gate. The cells can also be things like multiplexers and so on. Here in the AND, we have one input that is public and one input that is tainted. In this case, let's say the tainted input is secret data. The output of the AND will always be 0. Thus, we cannot learn anything about the secret in this case. In another case, when the known input to the AND gate is 1, then the output of the AND depends only on the tainted value. So in this case, the taint controls the output, thus we learn the secret, or an attacker could control the output. We use this then to specify the properties, and then we use, as said before, the model checker and either get a proof or a counterexample. So let's look at some instructions. If we have an add, we inject taint into the operand, and then the taint flows through the whole design. But if everything goes well, it never flows to the program counter. We could prove that. What about branches? Branches, as we have seen before, by specification, do change the program counter. So they would taint the program counter. And this is supposed to be a question mark. Is micro-CFI violated in this case? No, it isn't. What we do to avoid these cases, these known flows, is that we first classify instructions into different categories, and then we use different taint tracking logics. So for branches, they are allowed to have an indirect influence on the branch target or on the program counter. Thus, an implicit information flow is allowed by the specification, but no direct information flow from register operand into the program counter. And to be able to find only this kind of vulnerabilities where the branch target would be directly written into the program counter, we developed cell DFT, which is a variant of celllift. It tracks less information flows. So first I'll explain what celllift does. Celllift tracks all the information flows, timing, control, and data. So for example, on the multiplexer, if we have the select input tainted, then the output of the multiplexer will be tainted because now imagine an attacker can control the taint. It could control which of the two inputs is taken. In cell DFT, we block these kind of control flows. So if one of the inputs A or B would be tainted, that taint would still be propagating to the program counter. But if the select input is tainted, like a control path is tainted, we filter it out. We don't track the taint through these paths. And by that, if we get a cell DFT violation, it is, in our case, a control flow hijack. These are the detailed rules you find in the paper, how we implemented this. And then we categorize the instructions into these categories and verify, for example, the arithmetic ones with celllift, the control influencing ones with cell DFT, and the indirect jumps we don't verify at all because they're by specification supposed to change the program counter. So you should never let an attacker pass data to it anyway. The goals that we want to achieve with this is to now give a security classification per each instruction type for a given CPU, and basically telling you if you never pass a secret to these instruction types, then the software will be secure. So you could take a program that is constant time, and you can, with our security classification of instructions, then know if on a given CPU that program would be actually constant time, or if we know the ad is vulnerable, for example, then you should not pass a secret to the ad, although normally that's anyway a bug that happened. We verify this per instruction type, and instructions can be surrounded by any arbitrary instruction. That means we do still have branches in the sequence, but they just never have to read secret data. For better debugging, we are able to identify exactly the instruction that leaks the operand. And we make sure that we also take care of if one instruction influences the behavior of another one, we would catch these kind of bugs. Now let us look here as an example where we have two instructions. We have an operand that's tainted, and we have a flow to the program counter. How do we know which instruction tainted the program counter? We could look one by one. We could look after the ad and see that everything's fine, the program counter is untainted. Then we execute the CSR write, and we see that there is a taint flow. So now we would blame the CSR write instruction, the control status read write instruction. In reality, it could happen that there was a case like we have seen at the beginning, where the ads operand was changing the CSR write's behavior. So actually it was the ads operand that was leaking. And because of the classification, CSR writes are actually allowed to change the program counter implicitly. That's if we would get a cell lift violation, we would think that this is no violation at all and would miss such kind of bugs. So we can not do this approach of tainting the operand always and checking one by one. We need something else. What we do to solve this is that we precisely taint inject one instruction at a time. We write system Verilog assumptions that achieve this. It's one instruction at a time per sequence, but for every possible sequence that can be. We use a logic abstraction on the taint signal to achieve this, and then with the assumptions we create, we change when the taint is going to be entering into the design. And we do that based on reading conditions that are automatically generated from the design. So we don't need to rely on functional verification on when the CPU is expected to, when an instruction is expected to read from the register file, but we extract from a specific CPU design the condition when the instruction reads and when its value is updated again. So we don't also use the change value or something, because it could be reading the same value, or it could be the same instruction coming again, but we really generate this condition when potentially new data comes in, and then we taint. There's another case that we need to consider. Now we have two instructions here. We have an add that writes to a register, and then we have a branch reading from the same register. So again, we probably have an information flow from the add through the destination through branch to the program counter. To avoid these kind of, again, architecturally known and ISO-specified flows, we declassify these known flows, again, using a logic abstraction. And now we control the taint signal with assumptions again, but set it to be always 0, because these are the flows that are anyway known on architectural level and thus not microarchitectural violations. If we do this, we also need to consider the forwarded data as an additional input, because the instruction could read from that part. And here we use a trick. We still taint inject only on the operand when the data comes from the register, but we automatically identify the multiplexers in the design that decide whether data comes from the register file or from the forwarding path. And now, in the case that the CPU is in the state, it should receive data from the forwarding path. With the logic abstraction on this multiplexer, we verify both combinations. Either the multiplexer is choosing the forwarded path or the operand from the register. So it's kind of not really happening in the design, but we allow the taint going through. So with the abstraction, you always verify more scenarios. So in the end, the verification will also hold for the original design. And so that means in the case where everything points to forwarding, we let the taint from the register come in and thus verify also these cases, whether this instruction behaves differently in this case. And by doing so, we make sure that we don't block any other flows that are unexpected. we have verified this property on 4 RISC-V CPUs. Most interesting was the low-risk IBEX that's used in the open Titan root of trust. For all of them, per instruction, it took less than 24 hours per instruction. And this is all parallelized, so we have 1 instruction per task. So all of them are isolated. And we could prove many properties. So we could prove many instructions to be secure, also the crypto instruction of the Spark processor. But we also found multiple vulnerabilities on all of them. Some of them were already known. Some of them were new. For example, this running example that I had since the beginning, this was a timing side channel that we found on the Kronos CPU. Similarly, there was a control flow hijack. In both cases, it was possible that the immediate of the ad was taken as a CSR address, and then by the decoding, something weird happened, and the operand value of the ad ended up in some CSR register, like performance counter, like exception program counter. And on the IBEX one, we found also a constant time violation and a data leakage where the multiplication got in some weird stage. And then it was possible that data from one multiplication leaked to another, either really into the registers, or it could cause a timing delay of the next instruction of the next multiplication. And also a control flow hijack in some custom configuration, where this one was found with cell DFT, where a branch operand was really writing into the program counter. And that's particularly interesting because most of the constant time verification methods, they exclude branches. They don't allow secrets to be accessed by branches. But in our case, because of the declassification, we can access secrets kind of with the branch or attacker control data. We declassify the expected flows, and we still find this kind of bugs where an unexpected flow happens. That was it. So yeah, introduced MicroCFI now, and thank you, and open for questions.
Thank you very much for the talk. Do we have time for one question? Or
yeah, it's time for a question. And then can I just say, then it's, if everyone would like to go back to the main lecture theatre just for the wrap-up of the day, and then into pieces, students.
Okay, now first into the main lecture theatre and then into pieces.
Yes.
Okay, thank you. Are there questions?
I would have a question. I really believe that is the right approach to find security gaps in processes. Can you talk a little bit about how do you do it from a practical point of view? Do you use the formal interface of the processors? Do you write your own assertions, or?
I wrote own assertions. So, and here we generated these conditions for reading, and we also automatically find this forwarding multiplexer and so. So we don't use the interface. The existing interface captures the data too early for our property, in fact. And yeah, so here it's mostly automated, and the property then is very simple. So it's really just checking, is there taint in the program counter?
And I know that IBEX is probably one of the best verified processes in the world. Still, people seem to continuously find more issues with it. So even that is not secure. So to what scale can you go? I mean, probably out-of-order processors would be a problem, but let's take with in-order processors. I mean, the examples are rather on the small end. Did you run it on bigger ones? Do you run into convergence issues, or?
That's why we stayed with the small ones, because on the larger ones, yes, we ran into scalability issues, and we still have to think of how to either decompose the property or have some other methods for the taint tracking if we can like reduce some complexity there. So.
Cool. Okay, then thank you very much for the talk again. And then it continues in the lecture theatre.
Yeah, just for 5 minutes in the lecture theatre.
Okay.
Big board, right?
It's called a
in the CPU.